Hello, and welcome to Trump. My name is Brett Thompson. I'm here with James Gamache. Today we're going to discuss the Highspeed Eco technology. After today's demonstration, we're going to spend a little bit of time discussing any questions you might have, so please stick around. Let's get started. So, what is Highspeed Eco and what are its benefits? Traditionally, gains seen when cutting with nitrogen are somewhat offset by a substantial increase in assist gas usage. On thin materials, the speed gains were so big that this really didn't matter. You may use more gas per hour, but the increase in productivity far outpaced increases in assist gas costs. This only became an issue when material thickness increases. When cutting with fiber in particular, it became difficult to force the assist gas through the kerf for proper slag ejection. As a result, speed and quality would suffer. So there was little point in using nitrogen around 1/4 inch and up in carbon steel. With a standard nozzle, the distance from the sheet to the nozzle was so great that lots of pressure was required to push the gas through the kerf. A lot of the gas is deflected off the surface, making the process somewhat inefficient. With Highspeed Eco, a replaceable sleeve is pressed down, only when cutting, onto the surface, sealing off the kerf and making the most of the assist gas. The sleeve is then retracted by reverse gas pressure to keep the profile of the nozzle small. The effect is a big boost in cutting speed and assist gas savings. As a bonus, the edge quality is pristine with this technology, and the burr is minimal. Here we see a chart of assist gas consumption on various thicknesses of mild steel and stainless steel. For example, you can see that mild steel sees an average of 30% savings in assist gas consumption per hour when compared to standard processing. This will have a substantial impact on production costs. We saw in the previous slide a per hour reduction in the amount of gas being used, but we also see cut speed gains of up to 200% when compared to standard processes. The additional production is great, but think too how this affects gas usage. You're using less gas per hour, but increasing the amount of parts cut per hour. That makes the per part gas savings even more dramatic. Now that we've covered what Highspeed Eco is and its impact on production, let's see some parts being cut. We'll start with a 1/4 inch carbon steel part. Both will be cut with nitrogen, the first with a standard nozzle and the second with Highspeed Eco. So this is the standard process. This is a 2.7 nozzle. You can see there's a pierce, a reduced lead-in where the laser is somewhat pulsing and slowing until the cut is established before it actually takes off and cuts at maximum speed. And we're getting towards the ends, and there we're done with the standard processing 1/4 inch carbon steel. Now, James is loading up the next position, and you can see he's doing so visually through our drop and cut interface. So he's graphically placing the location of the next part, and it takes the guesswork out of putting the thing down in the right position. So now he's going to load up the Highspeed Eco nozzle. All of the nozzles that Trump uses for various purposes. Could be for Highspeed Eco, could be for Cool Line, could be for Bright Line Fiber. All these different processes can use the same nozzle changer. So we're able to access the thing repeatedly. So the nozzle moves into position. It's cleaning off the nozzle. And we use an 18 tray nozzle holder because we're able to unload and reload nozzles. So we could pause in the middle of one program, put away a nozzle we've been using, load up a different nozzle. So the Highspeed Eco nozzle is loaded. We're going to do a capacitive sensing calibration. Okay, it's happy, so what he's going to do next is move into the cut process. So we switch our camera positions. Now it's going to be the same part side by side, just with Highspeed Eco. And what you're going to see is a difference in not only the cut speed, but notice how much quicker the piercing process is. There's no reduced lead-in. The pierce is directly into the cut, so there's no transition period. Okay, so that was definitely a faster process. So obviously the part was processed a lot faster with Highspeed Eco, but let's have a look at its effect on production costs. So again, for an overview, there's obviously a big difference in the cut time, some due to the increase in cut speed, but some due to the pierce. Piercing can be a lot faster with Highspeed Eco. With the increase in productivity and decrease in gas pressure, we also saw a reduction of 89% of the assist gas used per part. What does this mean for production costs? When combining the increase in productivity with the reduction in the assist gas consumed, we see a per part cost reduction of 27%. Let's see how that breaks down. Now with standard cutting on a fast machine, it's no surprise to see that material costs still the primary expense in production. Assist gas though is still a close second. With Highspeed Eco, we really see the benefits. At this point, the cost is almost purely material related. The impact of nitrogen costs are now almost completely negated. But what's it like living with Highspeed Eco? What's unique about the nozzle itself? Trump holds a patent on Highspeed Eco, but the patent doesn't relate specifically to the process, but to the mechanics of the nozzle itself. With other solutions, the nozzle rides directly over the surface of the material. This is great in theory, but in practice, the nozzle is prone to hitting tip-ups and surface contaminants, causing constant stops in the program. Cutting something like diamond plate would be a nightmare. Not true with Highspeed Eco. Now this video is a great example of how flexible Highspeed Eco is. It's a practical function, not a marketing gimmick. The nozzle is forced down using gas pressure from the head. As mentioned before, we use the same in reverse to retract the nozzle. This allows it to ride on a cushion of gas, which avoids issues so common to cutting with similar processes. Now when we slow this thing down to a pretty insane rate frame per second, we see what the actual process looks like on the sheet. You'll see the nozzle actually following over top of those contours. So we position, we pierce, we go right back into the cut. There's nothing special that has to happen here. And so if you imagine a sheet where maybe you have some surface bulging, or maybe you have some random contaminants, maybe it's just a sheet that just refuses to lay flat, this is a technology that's going to allow us to maintain that flexibility. That's really important. So really the question becomes, if the nozzle is in contact with the surface, doesn't that mean you spend a lot of money replacing the nozzle? The answer is no, because Highspeed Eco isn't one single component. It's made up of 3 separately replaceable items. The sleeve, which is the most commonly replaced item, can be swapped out in just about 20 seconds or so. And my colleague James is actually going to show us how to do so. So if we see that the nozzle is a little bit tore up, the kit comes with a key. Use the key to take the little pin out of the inside. We swap out the sleeve and we put a new one in. It's as simple as that. And it's just done so on a per need basis. This is a relatively inexpensive component to be replaced, so it really keeps operational costs low. Thank you, James. We saw Highspeed Eco improve mild steel, but how does it do with stainless steel? Let's have a look at that. As we saw in the mild steel sample, we'll cut first with the standard table and then again with Highspeed Eco. Keep in mind the improvement we saw when piercing. It's going to be really, really obvious here. Now, full disclosure, what this process is the best quality process, which is bright line fiber. Now, with bright line fiber, we're actually using a much, much larger beam diameter, which is achieved through our delivery system. So though we lose some speed relative to the true standard process, the edge quality is far better than what you would typically get with nitrogen cutting stainless steel on a fiber laser. But what we want to see with Highspeed Eco is the same quality, but cut really, really quickly with really, really good gas utilization. And that's what we're going to see here. So there's your first part. That took around 42 seconds or so. So now James is going to use the drop and cut technology again to access that part from his library. And again, we're projecting an image of the piece over the sheet. So he's visually dropping this part. So if we're trying to squeeze the guy into a tight bit of contour, we can make sure we're doing so while utilizing all that sheet without potentially running off of the sheet. Okay, so now the program is starting. We're going again from using a standard nozzle to a Highspeed Eco nozzle. Same process again. We're going to unload one nozzle, we're going to load up the other. Again, it's important to remember that the shape of the nozzles, no matter which nozzle we're using, no matter which process we're using, are always going to be the same. So we're able to use the same nozzle changer. They're all interchangeable. So we do our control line, our capacitive sensing test. It's calibrated. Now she's ready to go. So again, you want to keep your eye on the pierce. The pierce is going to be one of the more obvious differences between this and the previous process. So you're right through the material. It's definitely a quicker cutting process, but that piercing time is really going to have a big impact on our throughput. It's not too big of a part, so it's going to be done with the thing pretty quickly, and it's done. Very, very quick with Highspeed Eco. Let's have a look at it. Now, of course, there's a big increase again in speed and a reduction in gas usage. Here, the effects were even more profound than before. We reduced the production time by 62% and the gas consumption by nearly 89%. Remember, the gas consumption is relative to the part. We're getting more parts per hour because of the additional increase in our cut process. So we're really, really reducing the production cost of this piece. 62% faster, 27% cheaper. It's nearly $34,000 per year savings when running 10,000 parts. It's a pretty reasonable size for a production run. Now let's look at the per part breakdown. Again, the per item reduction in cost is substantial. What's interesting to note is how low of a percentage the investment cost has become. That premium machine's really paying for itself at this point, down at 1.8%. Assist gas down to 4.17%. Really, really substantial impact on the production costs. Since Highspeed Eco has a sleeve that makes contact with the sheet, it's not unreasonable to ask, what do I do about all-night production? Clearly, there could be some issues there. The answer to that question is high speed. So Trumpf offers a nozzle that is functionally similar to Highspeed Eco, though without the touchdown sleeve. The cut speeds are nearly identical, and there's still a substantial savings on assist gas usage. This is a great tool for lights out operation because there's no need to replace the sleeve periodically. As this chart shows, the speeds with Highspeed and Highspeed Eco are very similar and often the exact same. There's even a substantial improvement in gas consumption relative to standard processing. Let's have a look at the part cut with Highspeed and again with Highspeed Eco. So the nozzle in a lot of ways is very similar. This is still Highspeed Eco. We're looking again at the original 1/4-inch carbon steel part. So you're not going to see any difference from the first time you saw Highspeed Eco cut this thing. But rather than using our standard process, we're going to go with a really automated sort of nozzle solution to still gain that sort of productivity increase, that sort of gas savings, while not sacrificing reliability over the course of lights out operation. So we're going through the same process we saw before. James is accessing the proper program, putting in the right position graphically. Now, it's back to unloading that nozzle, and really the geometry of it's very same, except the sleeve is not being pushed down and then retracted again. So similar geometry, but it's not actually sitting on the surface. So it's a process that's very reliable for all-night cutting. Control line calibration again. Now he's happy, so he's going to go ahead and close the old gate, and then we go into our production. So, should see a process that looks pretty similar to what we had before. All right, and we're done. Now, so there are no difference in the processing time. as we can see from the slide here. But there is a difference in the amount of assist gas being used. So technically, Highspeed Eco is a little bit cheaper, but still, over standard processing, we're seeing really, really big improvements in your production. It's all about production costs. Now, at this point, we've concluded the presentation portion. Be happy to answer any questions you might have. So you can see my email on this slide. It's brett.thompson@us.trumpf.com, and this is how you're able to send any questions that you might have. So please feel free to send those in. So the question we have one relating to the material range that we can cut at. So it's going to depend a little bit on the series of machine we're talking about, as well as the laser power that we're using. So with the 8 kilowatt, of course, we get a little bit more capacity. So for mild steel, we're looking at about 0.16 material to 0.5 inch with the 8 kilowatt version. With a 6 kilowatt, 0.16 to 0.38. So we have a pretty good range there. When it gets to stainless steel, range broadens a bit. So with 8 kilowatts, 0.16 to 1 inch. When we're talking about 6 kilowatts, we have 0.16 to 1 inch again. With the 3000 series machine, we're looking at 0.16 to 0.31 for mild steel, 0.16 to 0.375 for stainless. Now, we should note that with the 3 series machine, we're looking at delivery of Highspeed Eco on that technology in July of 2018. So right now, this is a technology that is specifically for the 5 series machine, but what you'll notice over time is that the technology is going to find its way to other processes, materials, these sort of things, just all development related. So do we have any other questions? Okay, just bear with me while I go through the good amount of parts that we have here. Now we have one question on the edge quality. Can we pop one of the pieces out? So James is going to pull one of the parts out, and he's going to show us what the edge quality looks like. Now, the edge quality is going to be pretty close to what we would see on stainless steel with bright line fiber. On carbon steel, the edge quality is going to be pretty close to the same. Really what's being affected is the burr. So the burr limit is quite a bit less. So you rub your fingers along the bottom side, it's not going to be sharp like you sort of expect with those 1 micron lasers where we have that nice long waist. Okay, let's pull the, there we go. Okay, so we're going to grab the 1/2 inch as well, so you can also see that piece. So this is the 1/2 inch Highspeed Eco sample, okay? Do we have the bright line fiber, the other part? And I want James to show you that just so you can see the difference between that piece and bright line fiber, because bright line fiber really came around first to address the quality limitations that we saw with fusion cutting. So you're gonna see that the quality between that Highspeed Eco part and bright line fiber are very similar. If you looked at a standard process, you would see that the smoothness goes away about halfway down the sheet and that there's going to be a burr. Doesn't exist with this technology, either one of them. But obviously the benefit here with Highspeed Eco is we can still use our small hot beam for performance. So going through the list again, and do bear with me because they're coming in quickly. So now we have a question about whether this is available for the 2030 3 kilowatt machine. At this point, it's not. It's just a 3 and 5 series technology. Actually, at this point, only a 5 series technology. But again, it will be available in July of 2018 for the 3 series machines. Only at 6 kilowatt. And so question, would it be faster on thinner stainless steels? The answer is probably. The reality is that we've only gone down to about 4 millimeter 0.16 materials because we're really kind of addressing where your running into that break-even point when it comes to the ejection of the materials. So it's more that mid-thick range. There's every possibility that it could be applicable on thinner materials. So yeah, 11, 12, it could be a benefit. We do have a question about gas purity. There's really no difference in the gases. Only the gas consumption is going to have an effect. Now, what that means to steel, to stainless steel, is very different. If we're talking about carbon steel, of course, that material has carbon in it. It is going to be prone to oxidation over at some point, so it will rust. Now, stainless steel, of course, we want to avoid that. So with stainless, we need to use a higher purity nitrogen to ensure that we keep the potential for rust propagation out of the material. So we would use a much higher purity nitrogen as a requirement. But honestly, when it comes to Highspeed Eco, or really any of the other processes here, there's really no impact in that regard. So interesting question. Does this only work with nitrogen? It only works with fusion cutting. Now, fusion cutting can come in other forms. And what we're going to see is when we start playing around with processes like compressed air cutting, that there will also be a benefit with compressed air getting into thicker, mild steel mostly. Stainless steel, yes, but it's really mostly appropriate because of the rust issue on stainless steel. But mid-thick, mild steels with compressed air become a possibility with this technology. So another interesting question. So how much does material quality impact the speed and quality? Honestly, the quality of the material obviously is going to have an impact on whether or not we can cut at the same rate of speed. Even if we go from a cold rolled steel to a hot rolled steel, it's going to have an impact on the cut. But when we get into these thicker ranges, that's really kind of where maybe the Highspeed Eco has less of a benefit to us than does the Brightline fiber technology. Brightline fiber can programmably change the beam diameter to a beam that is considerably larger, 4 or 5 times what we can get through light collimation. So it's really when you get into those thicker steels, maybe an A36 or so, where you worry about purity, where the Brightline fiber is going to be able to address process reliability. From a Highspeed Eco perspective, it's really all about gas utilization and quality. It's going to see the same sort of effects as we would with standard processing. So at this point, we're going to go ahead and kick off here. We definitely appreciate you all coming and spending some time looking at the the Highspeed Eco technology with us. And if you have any more questions, do feel free to keep sending those in to us. I'll be happy to respond to any questions that do come in today, tomorrow, doesn't matter. Actually, let's say Monday, because I'm kind of lazy. I don't like working through the weekends. But again, I do appreciate your time and look forward to any more questions that you might have.